In this lesson, we're going to look at some more theory in terms of electrostatics. The first one is we're going to try to figure out what's the difference between insulators and conductors and look at some specific types of conductors. First off, what we're going to do is realize that there's actually four categories. It's not just insulators and conductors. We actually get insulators, and we have sort of different levels of conductors. So something that's sort of a conductor but not quite is a semiconductor, and then you can see at the end one that's an awesome conductor is a superconductor. So let's go through sort of what they are quickly before we get into some equations and formulas and so on. So first off, it says, imagine we got two metal spheres, one charged and the other neutral. So let's suppose we have, something with a -3 charge, like 3 electrons, and let's suppose we have another one that's neutral. So what it's saying is, if we put an iron nail between them, so if we touch these together with metal, what would happen is, I'm going to change this one so it's a little bit better. So let's suppose we have 4 electrons. In the first one, we touch the two spheres together with an iron metal. Because the iron is a conductor, we should get 2 of the electrons moving to balance things out. So we then would end up with 2 electrons in each metal sphere. Okay, so they'd each have a net charge of -2. But if we would have done the exact same thing but used a rubber rod, so if we would have had our 4 electrons in the original and 0 in the other, and in this case we put a rubber rod in between, the rubber being an insulator, it's not going to likely move any electrons, so nothing would change. So the idea is, in general, most metals are good conductors. They allow electrons to move freely, where most other materials are usually insulators. And keep in mind that there is some sort of charge that even passes through the weakest or the strongest insulator or weakest conductor. There will still be usually a little bit, but usually not enough to make any difference. So let's figure out what a semiconductor is next. So a semiconductor, remember, if we go back to our chart, are semiconductors in between an insulator and a conductor. So semi, kind of think of it as half, so it's sort of halfway in between. So there are certain kind of materials that we classify as semiconductors. Silicone is one, germanium, carbon, selenium. There's all different types of elements that we consider as semiconductors. And each one sort of has different properties that makes it a conductor sometimes, and then other times it would make it an insulator. So for example, we use silicone in computer parts, computer chips and things like that. And the idea is usually silicone, depending on temperature, will act as a conductor if it's cold and not when it's warm, or vice versa. So things kind of change. So a lot of times temperature is all that helps make something conduct electricity or not. Other ones like selenium is kind of an interesting one. It works as a conductor only when it's in light. So in the dark conditions, it's an insulator, but in light, it conducts electricity. And that's actually what we use for photocopiers. So inside of a photocopier drum, the drum is made out of selenium. And what happens is when you photocopy and the light turns on, it makes it a conductor, and that makes the toner stick to wherever the letters are and make your copy. Where if it's dark, it skips it. So it's kind of cool how things like that can work for certain applications. Another name that we use for semiconductors sometimes is a metalloid. You might see or hear that, and a metalloid just sort of means sort of a metal. So we'd say selenium is a metalloid because it works in some conditions, not in others. And our last one that's on the chart is a superconductor, and these typically are what we'd classify as, almost perfect or terrific conductors that basically lose no energy. So in any kind of electricity transfer, we usually lose energy along the way. So when you plug in your extension cords to charge your iPhone, for example, the electricity coming out of the wall, as it goes down the cord, it loses less and less due to friction and heat and whatever. So by the time it gets to your phone, there's actually some electricity that gets lost. Some of that transfer energy is gone. And same thing that happens in a power line. So when our power goes from EPCOR to our house, it loses some along the way. Okay, so a superconductor, basically the idea is nothing gets lost. Pretty much all the energy passes perfectly through the conductor. The negatives to superconductors is they typically only work when it's super cold, when it's near absolute zero, which would be 0 degrees Kelvin or minus 273 Celsius. Recently, though, they're starting to make ceramic superconductors, so they're sort of made out of ceramic tile type material, and they work well in about the minus 200 range, which is about the temperature of liquid nitrogen, which is way more practical and more affordable. So they're starting to use more of those kind of things for superconductivity. Type of applications would be, things like, super high-end NASA spaceship kind of things, or computer servers, and, pretty high-end applications. But in the real world, we typically don't deal too much with superconductors. Why do some things conduct electricity and others not? Why does a conductor work better than an insulator, and so on? So we're just going to look to kind of see how things work. So at an atomic level, remember we have our electrons orbiting the nucleus. We have our electrons somewhere way out beyond the nucleus. So those electrons are free to move around in terms of a conductor. In an insulator, those are pretty tightly bound to the nucleus. So some people sort of explain it as, so in a conductor, those electrons are sort of weak bonds between the nucleus and the electrons, so it's easy to take those electrons away or add them. In an insulator, we think of the electrons not necessarily being closer, but a stronger bond to the nucleus, so we can't get those electrons to move away as freely. So that's kind of the key idea, and remember, it's the electrons that are moving, not the protons. The protons in the nucleus are tightly packed, they're pretty solid, it's pretty tough to get those protons to leave the nucleus. It's only the electrons that we can add or take away. So we're going to go through some basic diagrams today and in the next lesson that'll sort of help you visualize what's going on here. So the first thing we're going to look at is what happens when we have a positively charged object move towards something neutral. So in this case, our rod, we have a red rod that's positively charged. As we get it closer and closer to something neutral, what happens is all the electrons, so remember imagine in a neutral object we have our positives and our protons and electrons. Let's assume they're fairly evenly spaced throughout the entire metal. Okay, so we have sort of an equal balance. But what happens is as soon as we bring something positive close to it, most of the electrons are free to move. They're going to pile up on the end that's closest to that positive object. So it's not like the protons are getting pushed away, right? There's still going to be positives over here. So maybe this diagram isn't too accurate, but so our positives are equally spread out throughout the whole thing. So let me just kind of finish off this diagram. So let's suppose that's our spread of neutral items. So the positives will stay there, but what's going to happen is all of those negatives, the electrons, the ones that are way over on the far end, are going to move to the close side. So the electrons will move, which would make, in essence, it would make this end negative, and it would leave the other end positive because there's no more electrons there. Okay, so what we do is we call that a charge separation. So even though it's one object and it's still neutral, the charges have separated. The electrons have all piled up on one end, making one end negative and the other end positive. And the same thing would happen in reverse when we bring a negatively charged rod. So if this rod that's negatively charged comes close, what it's going to do is the reverse. It's going to chase all the electrons away, so all the electrons pile up on the one end, leaving the other end just positive, which would then create charge separation once again. And lastly, just to kind of keep it in an idea, if it was an insulator, so if we looked at that last example, I was showing you conductors. So if these were insulators, those positive and negatives are tightly packed, they're not free to move. We brought the positive or negatively charged object to them, nothing's going to move, or very little, so not enough to make a difference. And in terms of a semiconductor, some of them there's only a few electrons that would move, and not very many, and depending on conditions, right? If it was cold, maybe there's a few more that are going to move. If it's warm, less, and so on. But in insulator, basically none. And so usually with those kind of objects, if we bring something charged to it, nothing happens. And that's it.